this video, we're going to go a little bit deeper into the sinusoidal nature of simple harmonic motion. Simple harmonic motion is closely related to circular motion. For example, if you glued a small ball to a turntable and looked at the shadow of the ball's motion projected on a screen, the ball's shadow, which is shown in blue, would be in simple harmonic motion. The second picture gives us another view. As the black dot follows a circular path, we just discussed how the motion on the x-axis is simple harmonic motion. But now we can see that the y component is also in simple harmonic motion. This also shows the sinusoidal graph that is produced when something is in circular or simple harmonic motion. This graph shows that one complete oscillation is equal to 2 pi radians, the distance around the trig unit circle. In this lesson, we're going to discuss 3 equations that relate displacement, velocity, and acceleration to time. These equations are derived from circular motion. And I point all of this out because you may already have some experience graphing the trig unit circle as a sinusoidal function in your math class. And if so, this topic is very similar. We've looked at this graph before, but let's do a quick review. This graph shows a mass on a spring oscillating up and down. Pretend that we taped a magic marker to the mass, and then someone started pulling a roll of paper across the room. As the mass oscillates, the magic marker would show the sinusoidal path of the block's motion. The x-axis on this graph shows time, and the y-axis shows displacement x from equilibrium. And yes, it can be a little bit confusing that we're graphing x on the y-axis. And the starting position of the wave on the y-axis tells us the initial position of the mass. In many cases, the initial position is one of the endpoints or at equilibrium. So then the question becomes, as the mass oscillates up and down, where exactly is the mass at any given time? The position function can tell us the exact location of the mass. The position function can be written as x equals a sine omega t or x equals a cosine omega t. Let's talk through this form of the equation. So x is actually what we're solving for. That is going to tell us the exact location of the mass on the y-axis as it oscillates up and down. A is the amplitude of oscillation, which we can read off the graph. And sine or cosine, that depends on where the mass starts. So if the mass is starting at equilibrium, or if the graph is starting at equilibrium, we're going to use the sine function. And if my mass is at a negative endpoint or a positive endpoint, I'm going to use the cosine version. And then omega is angular frequency, which means we're going to calculate that, and it's going to be equal to 2 pi times the frequency. Given the position function with respect to time, we can use calculus to determine the velocity and acceleration functions. Let's start by writing down the position functions. We know there are 2 forms depending on the initial location of the mass. In the next row, we're going to be writing the velocity functions. Velocity is the slope of a position time graph. So in calculus terms, we can get the velocity by taking the derivative of the position function. And in this case, that's going to involve using the chain rule. Let's start by looking at these derivative statements. This reminds us that the derivative of the sine of something is equal to cosine of that something. And the derivative of cosine of x is equal to negative sine of x. So let's write down the velocity functions and explain how we got them. In this case, we have sine of omega t. So omega t is like x in this statement. So the derivative of sine of omega t is cosine of omega t. And then the chain rule says that we also have to take the derivative of the inside term. So derivative of omega t is omega, and because that's a constant, we're going to pull that out front. So this is the velocity function, which is the derivative of this position function. Let's do the same thing on the other side. So here we have cosine of omega t, and the derivative of cosine of omega t is negative sine of omega t. And again, we take the derivative of omega t, which is omega, and that's how that ends up out front. And now to get the acceleration functions, we're going to take the derivative of these velocity functions. So here we have cosine of omega t is negative sine of omega t, and we took the derivative of the inside term and got an omega, and we already had an omega, so that's where the omega squared came from. On the other side, we have sine of omega t is cosine of omega t, and we did the derivative of omega t and got the omega, so we have the omega squared. You'll also notice that both the acceleration functions turned out to be negative, and that's because this initial displacement was positive, and the acceleration always acts in the opposite direction. If the initial displacement had been negative, the resulting accelerations would have been positive. In the middle row, we have what I call the simplified equations. These equations result when this phase term here turns out to be 1, which can happen when the mass is at an endpoint or at equilibrium. And these equations provide a quick way to calculate the maximum velocity and/or maximum acceleration of the oscillating mass. And the last thing is just a reminder that when you use any of the sine and cosine equations in this table, your calculator needs to be in radian mode. I also want to point out that we can get more precise values for the position, velocity, and acceleration if we replace the omega with 2 pi f. In fact, sometimes answers are even stated in terms of pi. You should be able to recognize and use the equations either way. So let's look at an example so you can see how all this can be helpful. A spring stretches 0.15 meters when a 0.3 kilogram mass is hung from it. The spring is then stretched an additional 0.1 meters from this equilibrium point and released, causing the system to oscillate in simple harmonic motion. Calculate the spring constant, period of oscillation, angular frequency, and amplitude of oscillation. So we've answered questions like this before, but we're going to need these answers to go on. So let's work through them quickly. So letter A, to find the spring constant, that hanging down mass is causing the restoring force. So 0.3 times 9.8 equals kx, and we find out that the spring constant is 19.6 newtons per meter. Determine the period of oscillation. We can find the period of oscillation from the period equation, where 2 pi equals the square root of m over k, and the mass is 0.3, k is 19.6, and we find out that the period is 0.78 seconds. We can get the angular frequency from frequencies 1 over period, so the angular frequency, which is 2 pi f, would be 2 pi 1 over t, or about 8.06 radians per second. But I also want to remind you that there's another way to find angular frequency, and the angular frequency is also equal to the square root of k over m. And if I do it that way, I get 8.08 radians per second. There's less round-off error doing it this way, so I'm going to use this answer going forward. Letter D, what is the amplitude of oscillation? And it says that we are stretching it an additional 0.1 meters and releasing it, causing it to oscillate. So the 0.1 meters is the amplitude, and it is negative because it's already hanging down, and I'm pulling it down further in order to set it into oscillation. Part E says determine the maximum velocity. So you can see that I've taken my space and divided it into 2 parts because I now want to show you that you have 2 different ways to answer this question. So prior to this lesson, we would have answered this question using conservation of energy. So it says that spring was stretched an additional 0.1 meters. So we are now at an end point, and at an end point, all of our energy is potential. So the potential energy is 1/2 kx squared, and we find the potential energy is 0.098 joules. So this is also the total energy of the system. And then as the system swings towards equilibrium, all of the potential energy turns into kinetic energy. So the kinetic energy is now 0.098 joules equals 1/2 mv squared, and the velocity is 0.81 meters per second. But another way to answer this question is to use our new relationship where velocity equals the amplitude times the angular frequency. Amplitude is 0.1, angular frequency is 8.08, and we also get a velocity of 0.81 meters per second. Either way is fine, but maybe you'll find the new way a little bit shorter. Letter F says determine the maximum acceleration. Again, let's find the answer two different ways. So we can get the acceleration from F equals ma, where the net force is the restoring force. And since I want the maximum acceleration, I'm going to make sure for kx that I put in the maximum displacement, which is the 0.1 meters. So solving for the acceleration, we get 6.53 meters per second squared. But we could also find the acceleration using our new equation that the acceleration is equal to the negative amplitude times angular frequency squared. So I'm keeping the negative sign. My amplitude also happens to be negative 0.10 times 8.08 squared, and I get an acceleration of 6.53 meters per second squared again. So the answers are matching, and it's maybe a toss-up in terms of which one's easier in this case. Letter G says, sketch two periods of the position time, velocity time, and acceleration time graphs. So these are the answers, but let's talk through how you would answer this question. I think it's always easiest to start with the position or displacement time graph. So let's look at that. So we know that we started the system in oscillation by pulling it down negative 0.1 meters. So I'm down here at an end point. So I'm just going to sketch an oscillation. So going up and coming back down would be one oscillation. And since I pulled it down negative 0.1, I know that it's going to go up positive 0.1. And so when I complete this first oscillation, that is one period, the time for a complete oscillation. And we calculated the period back in letter B, and that was 0.78 seconds. So I now can label that on the x-axis. And since I have to graph two periods, 2 times 0.78 is 1.56. So now when I go back up and come back down, I should be at 1.56 seconds. So sketching out the displacement time graph is pretty straightforward in terms of plotting out the periods and plotting the amplitudes on the y-axis. When you get to the velocity time graph, it can be a little bit tricky, but one of the things to remember is that the velocity time graph is shifted pi over 2 radians from the displacement time graph. So if we go back to the displacement time graph and we take that first oscillation and we divide it into fourths, where this is pi over 2, this is pi, this is 3 pi over 2, and then this is 2 pi radians. If we go back to this pi over 2, that's where the velocity time graph will start. So this tells me that the velocity time graph is going to look like this, and I can graph out my two oscillations. But let's also think about it a different way, that when you are at the displacement time graph and you're down here at this end point, we know that down here at this end point, the velocity is 0. So that's another way we're going to remember that the velocity time graph has to start at 0. And then we do our first oscillation, and we know that's going to be 0.78 seconds, and our second oscillation is going to take us to 1.56. How are we going to get these values on the y-axis? We actually just calculated them in the previous couple of questions. So it goes up 0.81 meters per second, and it goes down negative 0.81 meters per second. When we get to the acceleration time graph, we remember that the acceleration time graph is the same as the displacement time graph. It's just flipped upside down. Because when I pull it down a negative 0.1, when I pull it down in the negative x direction, we know that the restoring force and the acceleration have to be positive according to Hooke's law. So it's going to be the same shape, just flipped upside down, and we're going to keep the 0.78 seconds and the 1.56 seconds for period on the x-axis. And then the values for the y-axis we just calculated in the previous question, and that is positive 6.53 and negative 6.53. Letter H says write an equation for the position of the mass as a function of time. So this is our standard position function. We know there's two forms, a sine and a cosine form. And since we are at an end point at the start of the story, we know that has to be the cosine form. So now all we have to do is replace the amplitude and the omega with our values. Our amplitude is -0.1 and omega is 8.08. We're going to leave the t so that we can plug in any time that we want to calculate the position at that time. So letter I says calculate the position of the mass at a time of 0.7 seconds. So now we're going to plug in 0.7 seconds. So cosine of that quantity multiplied then by our negative amplitude. And remember, the calculator has to be in radians, and we get a position of -0.081 meters from equilibrium. Letter J says determine the velocity of the mass at 0.7 seconds. So to get the velocity, we're going to have to start with the position function and take the derivative of the position function. You can't keep looking it up in the table. You need to be able to take the derivative yourself to get the velocity function. So let's talk through it. I remind you that the derivative of cosine of x is negative sine of x. So the derivative of cosine of omega t is going to be negative sine of omega t. And then taking the derivative of omega t, we get omega, and we pull that out. So now that we have written the velocity function, let's use it to find the velocity of the mass at 0.7 seconds. So we're going to plug 0.7 in for time. We're going to plug our amplitude. We already have a negative sign, and our amplitude is -0.1. Omega is 8.08 times sine of 8.08 times 0.7 seconds. Doing all of our number crunching. Remember, calculator in radians. I got an answer of -0.47 meters per second. And letter K says determine the acceleration of the mass at 0.7 seconds. So again, we start with our position function. We worked our way to the velocity function. And now we're going to take the derivative of the velocity function to get the acceleration function. The derivative of sine of x is cosine of x. So sine of omega t is going to become cosine of omega t. And then we take the derivative of omega t and get omega, and that's why that becomes omega squared. So now let's use that and plug in our values of 0.7 seconds. So we have a negative sign already out front. Our amplitude is -0.1. Omega is 8.08. We have to square that. Cosine of omega t, 8.08 times 0.7 seconds. Again, calculator in radians, and I get an acceleration of 5.29 meters per second squared. So now let's check our answers by looking at them on our sketched graphs. So I copied the displacement, velocity, and acceleration time graphs here, and we plotted out our answers. So we calculated that at a time of 0.7 seconds, we calculated displacement of -0.08 meters. So this is 0.78 seconds. So backing up a little bit to call it 0.7 seconds, we calculated a -0.08, and that seems to line up with my displacement graph. We calculated a velocity of -0.47, so again we're in the negative direction, -0.47, and we got a positive acceleration value, and that also seems to line up with our graph.